In the previous class, we studied what is channel capacity and looked at the procedure to calculate the same for a binary symmetric channel and an R-array symmetric channel. We also looked at a definition of uniform channel as a channel whose channel matrix consists of rows and columns which are permutation of the first row. In literature, this uniform channel is also known as a symmetric channel. Today, we will look at the procedure to calculate the channel capacity for a few more channels of importance. One such channel is a weakly symmetric channel. So, let us look at the definition for the same. A channel is said to be weakly symmetric if every row of the channel matrix P is a permutation of every other row and all columns sums, that is probability of Bj given Ai for all I are equal. For example, a channel with a channel matrix given by 1/3, 1/6, half, 1/3, half, 1/6. In this channel, both the rows are permutations of each other and the sum of column is equal to 2/3 for j equal to 1, 2 and 3. This channel is weakly symmetric, but not symmetric. Let us calculate the capacity for a weakly symmetric channel. Mutual information by definition is equal to H b minus H of b given A, and capacity of a channel is maximum of I A semicolon b over input probabilities. So, let us look at the calculation of first H of b given A. H of b given A is equal to probability of A multiplied by summation probability of b given A log of 1 by probability of b given A summation over b summation over A. Now, the summation over b is a summation for each Ai of the terms in the ith row of the channel matrix. Now, for a weakly symmetric channel, however, this summation is independent of I. So, in that case, I of A semicolon B will be always less than equal to log of mod B minus H of rho of matrix P. Mod B is the size of the output alphabet B. We know that the maximum value of HB is equal to log times the size of the alphabet. So, and this quantity is H of rho of channel matrix P. Now, equality will hold if and only if the output distribution is uniform, in which case we will get the capacity for the channel. Now, in this case equality will, it can be shown in this case it can be shown that if probability of AI is equal to 1 by mod A, where by definition again mod A is equal to size of the input alphabet A, then if PAI is equal to 1 by AI, then this distribution achieves a uniform distribution on B. This is very clear if we note that probability of Bj is equal to probability of Bj given AI multiplied by probability of AI summed over A. This is equal to 1 by mod A probability of Bj given AI sum over A. Now, for a weakly symmetric channel, this quantity is constant for each Bj. So, this can be written as a constant which is C by mod A, and since this is true for all j equal to 1 to S, where S denotes the size of the output alphabet B, then this can be written as 1 by the size of output alphabet B. So, therefore, capacity for a weakly symmetric channel is equal to log of mod B. Mod B denotes the size of the output alphabet minus H times rho of channel matrix P, and this capacity is achieved for the input distribution which is uniform. Now, another channel, now let us look at the capacity for a noiseless channel. We had seen earlier that mutual information of a noiseless channel is given by H of A. Therefore, capacity for a noiseless channel is maximum I semicolon B over PAI is equal to maximum H A over PAI, and this is equal to log of mod A, where mod A denotes the size of the input alphabet A. So, if we have a noiseless binary channel, the capacity of a noiseless binary channel will be equal to 1 bit. Another important channel of practical use is binary eraser channel. This is the analog of the binary symmetric channel, in which some bits are lost rather than corrupted. In the binary eraser channel, that is BEC, a fraction of p of the bits are erased. The receiver knows which bits have been erased. The BEC has two inputs and three outputs. The channel diagram for binary eraser channel is as follows. We have two inputs 0 and 1, and we have three outputs 0, E, which denotes the erased bit, and 1. This probability is given by P. This probability, if it is a symmetric binary eraser channel, is again P. Therefore, this is 1 minus P and 1 minus P. So, let us calculate the capacity of a binary eraser channel. The channel matrix for this channel will be as follows: 1 minus P, P 0, 0, P 1 minus P. Let us assume probability of 0 at the input is equal to alpha, and probability of 1 is equal to 1 minus alpha. So, calculation of the capacity requires calculation of mutual information and maximum over AI. So, this is equal to maximum of PAI of H of B minus H of B given A. Let us look at the calculation for H of B given A. This is equal to minus double summation probability of AI, probability of Bj given AI, log of probability Bj given AI, from this channel matrix, and with this probability model for the input alphabet A, we get H of B given A equal to minus alpha 1 minus P log 1 minus P plus P log P. This quantity corresponds to the first row of the channel matrix. Minus 1 minus alpha P log P plus 1 minus P log 1 minus p, and this can be simplified as h of p. Now, to calculate h of b, we need to calculate output probability distribution. So, probability of B 1 is equal to alpha 1 minus p, probability of B 2 is equal to alpha p plus 1 minus alpha p is equal to p, and probability of B 3 is equal to 1 minus alpha into 1 minus p. Using this probabilities, we can show that h of b is equal to minus 1 minus p alpha log alpha minus 1 minus p into 1 minus alpha log of 1 minus alpha plus h of p. Therefore, finally, to calculate C, which is equal to maximum of P A I A semicolon B, this is equal to 1 minus p into minus alpha log alpha minus 1 minus alpha log 1 minus alpha. So, maximum over alpha. Although we can determine the optimal value of alpha by taking the derivative of I A semicolon b with respect to alpha and equating to 0, we can find it directly from the expression for mutual information I A semicolon b by realizing that the part between the curly bracket is really h alpha, and therefore, its maximum value is 1, and hence C is equal to 1 minus p, and this value is achieved when alpha is equal to half, that is the input probability distribution is uniform. Now, another channel of importance is known as Z channel. For this model of a binary channel, it is assumed that exactly one of the two input symbols, say A1, is transmitted without errors, while the other symbol, say A2, may be incorrectly received with a probability p. So, the channel model for such a channel is depicted in the figure as shown here. A1 and A2 are input alphabet, B1 and B2 are the output alphabet. This probability is 1, this is P, and this is 1 minus P. So, the channel matrix for this channel is denoted by 1 0 P 1 minus P. Let us determine the channel capacity for the Z channel with the assumption that probability of A1 is equal to 1 minus alpha and probability of A2 is equal to alpha. So, as usual, we require to calculate mutual information, which is H b minus H of b given A. So, calculation of H b requires calculation of probability of output symbols B1 and B2, which is given by P of B1 is equal to 1 minus alpha plus alpha P, and probability of B2 is equal to alpha into 1 minus P. Using this probabilities, we can write down H of B as minus 1 minus alpha plus alpha P log of 1 minus alpha plus alpha P minus alpha times 1 minus P log of alpha times 1 minus P. The second quantity which we require to calculate is H of B given A. Using this channel matrix and using this input probability model, we can easily write down H of B given A is equal to minus alpha P log P minus alpha 1 minus P log of 1 minus P. Therefore, we get mutual information I A semicolon B equal to minus 1 minus alpha plus alpha P log of 1 minus alpha plus alpha P minus alpha 1 minus P log of alpha plus alpha P log P. This is the expression which we get after subtracting this quantity from this quantity and simplifying. Now, in order to calculate the capacity, we have to take the derivative of this quantity with respect to the variable alpha. So, if we take the derivative of I A semicolon B with respect to alpha and then equate to 0, this will imply that 1 minus P into log of 1 minus alpha plus alpha P minus 1 minus P log alpha plus P log P is equal to 0, and this on solving for the optimum value of alpha, which we call it as alpha naught, we get the relationship as follows. So, if we take this relationship of alpha naught and plug it into the channel capacity expression, which is given by 1 minus alpha naught plus alpha naught p log of 1 minus alpha naught plus alpha naught p minus alpha naught 1 minus p log alpha naught plus alpha naught p log p, we get capacity equal to minus log alpha naught minus p times p by p minus 1 log of p is equal to log of 1 minus p plus p raised to p upon p minus 1 minus p by p minus 1 log p. So, this is the final expression which we get for the channel capacity for a Z channel. Earlier we have looked at the procedure to calculate the channel capacity for a binary symmetric channel. Let us look at the methodology to calculate the channel capacity for a general binary channel which is non-symmetric. So, if we have a binary channel with a channel matrix given by p equal to p 11, p 12, p 21, p 22, where p 12 is not necessarily equal to p 21, and we assume that input alphabet p a 1 is equal to alpha. So, p of a 2 is equal to 1 minus alpha, and for the output alphabet b, probability of b 1 is equal to beta. So, probability of b 2 is equal to 1 minus beta. For calculation of capacity for such a general binary channel, we will need to calculate h of b. So, h of b can be calculated if we define h 1 as minus p 11 log of p 11 minus p 12 log p 12, and h 2 defined as entropy of this row, which is minus p 21 log p 21 minus p 22 log p 22. Once we have h 1 and h 2, we obtain h b as minus b b, and h of b given a is equal to alpha times h 1 plus 1 minus alpha times h 2, which is equal to h 2 plus alpha times h 1 minus h 2. Now, for this we get the mutual information I a semicolon b, which is equal to h of b minus h of b given a as h of b minus H2 minus alpha times H1 minus H2. Now, with this channel matrix and with this input probability distribution, probability of B1, which is equal to beta, can be easily calculated as alpha times P11 plus 1 minus alpha P21, and from this it implies that alpha is equal to beta times minus P21 upon P11 minus P21. Now, all these entropies can be depicted in a figure as shown here. In this figure, the length of dg represents the value of entropy of the output alphabet, that is HB. The length of AB represents the value of H2. Similarly, the length Km represents the value of H1. Therefore, Lm which is equal to Km minus Kl is equal to H1 minus H2. Now, triangle BEF and triangle BLM are symmetric. Therefore, BE upon BL is equal to EF upon LM. Now, BE upon BL from this figure is clearly equal to beta minus P21 upon P11 minus P21, which is equal to alpha. Hence, EF is equal to alpha times H1 minus H2. Now, Fg is equal to dg minus de minus Ef. This is equal to Hb minus H2 minus alpha times H1 minus H2, which is equal to mutual information A semicolon B. So, in order to obtain the capacity for a general binary channel, which is equal to the maximum of I A semicolon B over P A I, we find channel capacity C by drawing a line parallel to B M and tangent to this curve, which is a entropy function. The point of contact determines the value of B naught of B of beta that belongs to the capacity. So, the optimal probability distribution of the source is therefore given by probability of A1 is equal to beta naught minus P21 upon P11 minus P21 is equal to alpha naught. So, this will be a general procedure to calculate the capacity of a binary channel based on a graphical approach. Now, as a final example of our exercise in calculation of channel capacity, let us take a channel with input alphabet consisting of two symbols A1 and A2 and output alphabet B consisting of three symbols B1, B2, B3 with the channel matrix given as half, half, 0, half, 1/4 and 1/4. So, for this probability of A1 is equal to alpha and probability of A2 is equal to 1 minus alpha. Now, for this channel, the channel diagram can be drawn as follows. So, in order to calculate the capacity, we need to calculate the mutual information, for which we need to calculate H of B, which in turn demands that we calculate the output probabilities of the symbols B1, B2 and B3. Probability of Bj is equal to probability of Bj given Ai multiplied by probability Ai, I is equal to 1 to 2, which is equal to Pij multiplied by Pai, I equal to 1 to 2. For the given channel matrix, we can show that probability of B1 is equal to half alpha plus half 1 minus alpha is equal to half. Probability of B2 is equal to half alpha plus 1/4 1 minus alpha is equal to 1 plus alpha by 4, and finally, probability of B3 is equal to 0 multiplied by alpha plus 1/4 multiplied by 1 minus alpha. Given these probabilities, we can calculate H of B, which is equal to minus half log half minus 1 plus alpha by 4 log of 1 plus alpha by 4 minus 1 minus alpha by 4 log of 1 minus alpha by 4, and this can be simplified as equal to 3 by 2 minus 1 plus alpha by 4 log of 1 plus alpha minus 1 minus alpha by 4 log of 1 minus alpha bits per symbol. Next step is to calculate h of b given a, which is equal to double summation of probability b j given a I log of probability b j given a I multiplied by probability of a I equal to 1 to 2, j equal to 1 to 3. For the given channel matrix, we can show that this quantity is equal to minus alpha times half log half plus half log half minus 1 minus alpha half log of 1 by 2 plus 1 by 4 log of 1 by 4 plus 1 by 4 log of 1 by 4, and this can be simplified as equal to alpha plus 1 minus alpha times 3 by 2 is equal to 3 by 2 minus alpha by 2. So, finally, we get mutual information as h b minus h of b given a equal to minus 1 plus alpha by 4 log of 1 plus alpha minus 1 minus alpha by 4 log of 1 minus alpha plus alpha by 2. Now, channel capacity is maximum of I a semicolon b over p a I, which is equivalent to maximum over alpha. Therefore, this implies I a semicolon b equal to 0, which implies that minus 1/4 log of 1 plus alpha minus log e by 4 plus 1 by 4 log 1 minus alpha plus log e times log e by 4 plus half is equal to 0, which implies log of 1 plus alpha upon 1 minus alpha is equal to 2. Therefore, the optimum value of alpha is equal to 3 by 5, and if we plug in this value into the mutual information, which is given by this expression, where alpha is substituted by alpha naught, that is the optimum value, then we get the channel capacity as 0.16 bit per symbol use. So, now we have looked at a very general procedure of calculating channel capacity for a channel. Now, in the next class we will begin our study which will lead to Shannon's second theorem, the most surprising as well as the most important single result of information theory. Shannon's second theorem deals with the amount of error-free information which we can get through a channel. We will also look at the relationship between the error probabilities and the mutual information in a channel.